Hi! In this tutorial, we want to show how to record, build a classifier and deploy it live. It will be shown using Monarch camera from Unispectral in PerClass Mira 4.0. In the latest release of PerClass Mira, a new dialog contains two panels. The first one is Scans in File and used for processing data. The PerClass project type is used for data acquired in PerClass Mira. Also, we can still find vendor-specific formats such as Kubert, Edwall, or Innospec, and so on. Unispectral project is used for data saved from the Unispectral GUI. The second panel is useful for live acquisition. This mode allows to select the camera to connect in order to record and save spectral data. In our case, we select Unispectral. In the source, we see that the plugin from Unispectral has been loaded and is ready to use. We can now initialize the camera and start the acquisition. In the upper part, the speed of the camera in frames per second and in milliseconds are displayed. As we want good quality data, we want to be sure that the sensor is not saturating by changing the view of spectral band. The red pattern is showing pixels higher than the maximum raw display value. So the goal is to decrease the exposure time until the sensor is not saturating anymore. It is better to check using a white reference. This is how we set the exposure parameter in order to get the highest dynamic range as possible for recording data. PerClass Mira provides three options for reflectance correction. The first one is not applying any correction. We get only raw data. The second one is done by a point spectrum. We can select our region of interest in the scan and set the mean of the region as a single spectrum. This is useful when the white reference is not covering the entire field of view, for example. It is the same for the dark reference. These point spectrum references will be embedded in the cube when saving data. In our case, we want to correct for non-uniformity, meaning per pixel correction. Once we define them, PerClass is creating a scan-specific correction, saving the entire cube for white and for dark references. As we defined the references, we are able to apply the correction per pixel in the acquisition panel. Our goal is to classify some almonds and some shells. We want to record some almonds and shells for building the classifier. We record more than only one scan to see the robustness of the classifier. When looking at stored data, we see that for scan-specific correction by area, we get the scan under PCF format and both references matching the scan name. This is how the data are stored. As we mentioned, now we want to build a classifier in the project. We first have to close the device in order to switch to processing mode. The scans that were added to the project are corrected per pixel. We had three classes for the background, the almond and the shell before labeling data in the scans. We see on the right part that the mean spectrum of shells and almonds are displayed. Once we label our data, we can search a model. Now that we obtain our classifier, we set our classes of interest, meaning almond and shell, classes as foreground by pressing F. As we want to define only one class per object, we switch the object mask from each foreground to all foreground, so that each object will be defined by the max fraction of the class. For improving a model, either you label more samples that are misclassified, or you can also apply some constraints in a confusion matrix. This is shown in another tutorial. In our case, we label and retrain the model by pressing R on the keyboard. To make sure that we have a good model, we look at other scans to see the decisions per object. We can conclude that in this case we obtain a good classifier. Once we build a good classifier, we can deploy and run it live. We initialize the camera and start it again. As the correction is already applied, we can from now on apply the classifier per pixel. Before segmenting out the objects, we must stop the camera. In the right upper part, we get the total speed, meaning the camera speed, and the classifier speed. In this example, segmentation of objects is running at 0.9 frames per second. In the last part, we want to show how to increase the total speed of processing by reducing number of bands. First, we need to close the device. Then, in Spectra panel, we select the most relevant bands and search for a model. The classifier will be built only using spectral information for these bands. We improve the classifier by labeling more data and retraining the model. For running the model live, we enabled the band reduction in the camera before initializing the camera. By reducing number of bands, we are now able to run at 1.5 frames per second. In fact, we are acquiring only the bands that we selected previously. Thank you for watching this tutorial.